Hello, welcome to my talk on understanding fluid motions, Lagrangian method. Generally, we have two very different approaches to describe the fluid motion, namely as Eulerian representation and Lagrangian representation. This talk aims on the Lagrangian method, thus a historical origin of these two methods will be introduced, and then we will discuss what is Lagrangian representation and why the motion parameters are not independent for x, y, and z. And we will see the similarities and the differences between the solid motion and the fluid motion. In the last, a discussion will be made for why we use the Lagrangian method for solid dynamics, but not for fluid dynamics. Why? As you may know, in fluid dynamics, we have two possible methods to describe fluid motion: the Eulerian representation and the Lagrangian representation. Historically, in 1757, Leonhard Euler derived the Euler equation for fluid dynamics, while Joseph Lagrange in 1788 formulated the classic mechanics mathematically. Principally, these two motion descriptions are very different, and later on these two methods were named as the Eulerian and the Lagrangian method, and these two methods were especially developed for fluid motion and solid motion respectively. This is still true today. Eulerian representation is the method mostly used in fluid dynamics, while the Lagrangian method is mostly used in solid motion. Although Lagrangian method occasionally used in fluid dynamics, this talk is on the Lagrangian method, but the purpose is for understanding the fluid motion better. So in the serious talk on the element fluid dynamics, I'm going to answer the following questions regarding the fluid motion and the fluid dynamics. The first question would be, what are the Lagrangian representation and the relevant independent parameters? This would be the topic in this talk. And what is the Eulerian representation and the relevant independent parameters? Why in fluid dynamics the Eulerian representation is most used? And for fluid dynamics, our ultimate target is to solve the detailed local fluid motion. But how? We will see different methods could be used for such a purpose in my talks. To understand the fluid motion, we need to compare how we can describe the solid motion. The first example is the motion of a mass point. We start from this simple example to explain what is the Lagrangian representation. For a point mass, its body size is much smaller than the motion trajectory, hence the rotation motion of the body is ignored. The examples include the flying balls, the planets. Here, we see the planets in the solar system. Although the planets can be huge, like the Earth we live on. However, in the solar system, the planet size can be ignored. Thus, can be taken as the point mass. The motion of a point mass can be simply expressed as the vector r with three components x, y, and z. Such a motion description is the Lagrangian representation, or the Lagrangian method, a method for tracing the motion path. If we obtain the position of the point mass, we can easily calculate the velocity given as this, and the acceleration given as this. The dynamic equation for the point mass can be quite easy. In fact, we may learn this in the secondary schools. The dynamic equation for the point mass is based on the Newton's second law of motion, given as this, and the problem can be solved if the inertial condition given as this and the force are given. As such, we can also write the dynamic equation into the component form given as this. Therefore, for such a system, we have 3 degrees of freedom, DOFs. This means the motion can be fully described using 3 variables, x, y, and z. Here, the example is for a ball which had the velocity v0 on the horizontal surface, and then the ball would have a free fall after leaving the surface. To solve the problem, we can assume the coordinate as this, and we take t equaling 0 at the ball leaving the horizontal surface. Thus, the dynamic equation would be given as this. This means the ball is subject to its gravitational force, mg. Here, the air friction is ignored, and the inertial conditions are given as this. X, y, and z are 0 at t equaling to 0, and Vx is v0. Vy and Vz are both 0 at t equaling to 0. For this simple problem, the solution would be given as this. Thus, the problem is very simple. We may have learned this in the secondary school. However, this is not my purpose in my talk using such a simple example. My purpose is for this question in the Lagrangian representation are the parameters x, y, and z independent. For this example, we have the solution in the previous slide given as this. And from the relation between x and t, we can obtain t equaling to x divided by v0. And substitute this relation into the last expression. We could build the relation between z and x given as this. And if we draw this trajectory, we could have the trajectory, the red line. So from this example, we can see z and x are not independent because z is a function of x. And this would be true for 3D motions. X, y, and z are not independent. In fact, in such a representation, the Lagrangian representation, on the trajectory, x, y, and z are all dependent on one parameter, the time t, which is the independent parameter in the Lagrangian representation. Here we assume a more complicated system given as this xt as a function of t as this, and zt is the function of t as this. So obviously we can't easily solve t from either xt or zt. Instead, we can still draw the trajectory if we use different t, here t from 0, 0.1 to 1. And we can get the corresponding x here in this column, z in this column. And then we can use the corresponding values of x and z. We can plot the trajectory as this. Obviously, this trajectory is complicated, but it is deterministic. And we can see from this trajectory, if we change x, z would change accordingly. This means z is dependent on x. So we can see if x and z are both the function of t, and in such a case z would not be independent of x. Here we look at another example. X is the function of t given as this, but here z is a random number. In Microsoft Excel, z is given as len bracket. So based on the principle in the previous slide, we can draw the plot z against x as this. So here we can see x is the function of t, but z is a random number which is not the function of t. Hence, the relation between x and z is not deterministic. In fact, we can obtain different plots every time when we redraw it in Excel. As such, we can say z is independent of x, since in here, when x changes, z could change, but not accordingly or deterministically. This means z is independent of x. Fluid motion has no similarities with the motion of a point mass, but would be quite similar to the motion of a rigid body. Thus here, the motion of a rigid body is discussed. Generally, we can discretize the body into many small elements, see the plot, and each element could be taken as a mass point. Suppose the mass of the element is mi and the total force acting on the element is Fi. This vector force Fi could include the internal and external force. Based on the Newton's second law of motion, we have the dynamic equation for the element given as this. And we can also put all these elements together, so the overall body motion can be expressed as this. Here, we can first calculate the total force acting on the rigid body, given as this. Here we can see the total force for the rigid body will be the external force only, the vector capital F, since all the internal force would cancel each other. And the left-hand side term of the equation, we can make some mathematical manipulation. So here, we can move mi into the second order differentiation with regard to t, since mi is independent of the time. And then we can make the exchange of the second order differentiation and the summation. So we have the expression as this. Now we can apply the definition of the center of gravity given as this. So sigma mi would be simply expressed as m rg. M is the total mass of the rigid body, and rg is the vector of the center of gravity. Since m, the total mass, is a constant, thus the second differentiation would be made on the vector rg. Put all this together, we can have the equation for the overall motion for the rigid body, the translational motion, given as this. Similar to the rigid body, in fluid, we need to discretize the fluid domain into many small elements, and each element is treated as a point mass. So similarly, the dynamic equation for the element would be given as this, following the Newton's second law of motion. We can do the summation as we have done for the rigid body, as this, and the total force acting on the whole fluid would be the external force, the vector capital F. However, in here for fluids, since the center of gravity is not as easy as that in the solids because of the sliding motion in fluids, generally we don't perform the similar study as that for the motion of the center of gravity of a rigid body. Here we will examine the fluid motion in terms of overall motion and the detailed local motion. If we take a large domain of fluid like this, we can see far away from the structure the airfoil in the fluid. The fluid would be uniform on the boundary of the large domain. Overall, we would know the fluid would generate a lift on the airfoil, and the airfoil would exert their force to the fluid based on the Newton's third law of motion. This is why the fluid near the airfoil would change the direction due to the force of the airfoil acting on the fluid, F1. However, this overall dynamic equation would not our target. Instead, in the application, we are far more interested in the details of the fluid around the airfoil, the local fluid field. And we are also only very interested in the lift generated by the fluid on the airfoil. In this regard, the fluid dynamic equation would be more given on the individual element given as this. This is the equation we are trying to solve for fluid motion. For the individual element, the fluid would move along its path line, the black line here. So the position of the element can be expressed by ST, by these three components, XX, YS, and ZS. The dynamic equation for the element would be given as this, or in detailed form as this. Here, the force F, or the force component Fx, Fy, and Fz are the total force acting on the fluid element. Based on Euler, the force acting on the element should include the body force and the surface force, mainly due to the fluid pressure and due to the fluid viscosity. Obviously, from this dynamic equation, if we have the fluid force, we can easily solve the trajectory of the fluid particles. And here, it should be noted similar to the motion of the point mass. The coordinates xs, ys, and zs would not be independent. They all depend on one parameter, the time t. So this is correct for the individual. And from the dynamic equation, we can see in the Lagrangian representation, the fluid description is simpler, at least in principle, since here the acceleration of the fluid particle is linear. If we compare it to the Eulerian representation, we will talk this in a different talk, where the acceleration is much more complicated with the nonlinear convective acceleration. And we know is this nonlinear convective acceleration term causes all the complicated flow problem in mathematics, including the fluid turbulence. So in this regard, the Lagrangian representation for the fluid motion is simpler. Then we might have a question, why we don't use this representation, the Lagrangian representation, for fluid dynamic problem. Here we look at the flow past an airfoil. We take two fluid particles, P1 and P2. So based on the flow, we can see these two particles would follow the fluid path line, the dashed line, the red line, and the black line. And the position of the particles can be described by x1t, y1t, z1t for particle 1, P1, and x2t, y2t, and z2t for particle 2, and so on. Obviously, if we want a good representation of the fluid motion or a meaningful representation of fluid motion, we need a very large number of such fluid particles. Here we can see for the steady flow, the path line and the streamline are coincident. A path line is the path of the fluid particles moving along, so it is the trajectory of the fluid particle movement. Thus, a path line can be seen as the time history of the fluid particle movement, while the streamline is a line on which the fluid velocity is tangent to it. Streamline is an instant line. If we take a snapshot of the fluid motion, and the line would be the streamline. It's an instant line, not the time history. However, in a steady flow, the path line and the streamlines would be coincident. Now, in the next two slides, we will compare the motion of the solid and the fluid. As we mentioned, we can describe the fluid domain or the rigid body into many small elements, and the dynamic equation would follow the Newton's second law of motion. In this regard, they would be same for fluids and solid. However, we have huge differences between fluid dynamics and solid dynamics. The main issue here is the fluids could flow or have a sliding motion, while solids do not. So in solids, the rigid body, the degrees of freedom would be 6, 3 translational motion plus 3 rotational motion. And in here, we are only interested in the translational motion, while the rotational motion is not very relevant. In the fluid, due to the sliding nature of the fluid element, so the degrees of freedom would be 3 times n, Here, the capital N is the number of the element. That means each element has 3 degrees of freedom, since each fluid element can be taken as a mass point. Also, due to the sliding nature, the fluid element must be small enough for a good and meaningful representation for the fluid motion. Thus, we need a very large number of fluid elements. In the study, tracing all these elements in fluid would be a huge task. In solid, because there is no relative sliding motion, so the motion would be much simpler. While in fluid, there could be very complicated relative motion, and for which the details we must focus on, such as the turbulent motion. This is actually what the fluid dynamics for, and this is why the fluid dynamics is so difficult. Fluid pressure and viscosity would introduce the motion-related surface force, but these are very difficult to be expressed in the Lagrangian representation. For instance, based on the reference here, the expressions of the viscous force of 3D flows in Lagrangian representation is still an open question. In the last slide, we will make a discussion on why in the fluid we are not using the Lagrangian representation. Because in the previous slides we have seen, for the motion description, the Lagrangian representation would be simpler than Eulerian representation. But why we are not using the Lagrangian representation for fluid dynamics? In the Lagrangian representation for fluids, the first difficulty, we need to trace a very large number of fluid elements, and this is in many cases well beyond the computer capacities. The fluid surface force for the fluid element, due to the fluid pressure and the viscosity, are difficult to be formulated in Lagrangian representation. As we mentioned this before, for 3D viscous flow, the dynamic equation in Lagrangian representation have not been derived yet. We have other issues for Lagrangian representation for fluid dynamics, including the fluid compressibility problem, since the point mass and its volume of the fluid element are not related. And so on, we have other issues with the Lagrangian representation for fluid dynamics. But overall, the first and second issues would make the difficulties for using Lagrangian representation in fluid dynamics.